Hi guys, welcome back. We've been talking about electronic configurations, and what's dawned on me as I've gone through it is we haven't really covered much about how the electrons are being populated into the shells. That's something I'm planning to do here, along with a couple of other things I'd like to kind of clarify. To help us with that, we've brought our old friends lithium and fluorine into the fold. And as you can see there, they look quite similar in terms of their uh, sort of state. So here you've got lithium. I'd actually re-recorded this video and put that X on there. So essentially, this is our lithium. So we've got the inner shell here. Let me get rid of that rubber. You've got the inner shell here, the shell 1, and it's got the 2 electrons in it there. And you've got the shell 2 here, and that's got a single electron in it. And that is lithium. So that is the natural state of lithium. That's the way you find lithium normally. That is the neutral, non-charged lithium. But make no mistake, you're not likely going to find lithium like that in nature for too much longer. Why? Because there is this shell number 2 here. So if I was to go back to my red pen and write out the electronic configuration of lithium, we know it's going to be 2 and we know it's going to be 1. Now, bearing in mind that the shell number 2 can take 8 electrons in it, and we've only got 1 electron in it. Now, that leaves lithium very highly reactive and unstable indeed in that state. In fact, lithium is very keen indeed to lose that electron. Think of lithium as being a kind of investor. Ideally, it would like to have either a full shell 2, but that's not going to happen. It would take too many electrons to fill that, and that's too much energy. So far easier for lithium to lose that electron. So this is where reactions start taking place. Lithium is not happy at all at just having a single electron in its second shell there. It is very keen to lose it. It wants to therefore donate that electron to another atom that can take it. On that note, let's take a look at fluorine over here. Now, fluorine's looking very, very bare indeed. Probably not such a bad thing because it allows me to show you something else while we're here. So what I'm going to do is start populating the electrons around fluorine. So if you remember that we need to get 9 electrons in the outermost shell of fluorine. Okay, so we need to start off with 1 there. Okay, 1 over there. That's number 2. Then we need number 3 up there. And then we need number 4 down here. Okay. So that's the sequence of putting the first 4 in, but we need to get some more in there. So without further ado, how do we do that? 1, 2, 3, 4, and then number 5 will therefore go up here. So that's going to be number 5 will populate down here. Number 6 will then populate down here. Number 7 will then populate over here. Okay. But we are stopping there because that's as far as it goes for the fluorine, the element. That's as far as it goes. So, ladies and gentlemen, boys and girls, we have got a kind of a bit of symmetry here. We've got lithium over here that's got the electron it wants to get rid of. And you've got fluorine over here that's now got, if we look at it here now, you've got the 2 and you have got the 7. Yeah? And it'd like to get to 2 and 8 as well. So at the end of the day, what isn't feasible is for lithium to go to 2 and 8 because there's too much energy involved there. So it's going to be far easier for lithium simply to go to 2 and give that extra electron away. And for fluorine, well, fluorine's got a couple of choices too. It could either lose all 7 of its electrons in the outermost shell, which is going to be an awful lot of energy and an awful lot of effort for fluorine to do, or quite simply take that electron that's wandered around from lithium and then go ahead and stick it in there. So what we could do is take that. Let me use another pen. What haven't I used yet? Oh, I'm running out of choices here. Let's just use green again. So what we could do is we could take that electron there that lithium's got to donate, and go whee all the way over to here, plonk it right up to there. There we are. And that would give us something called lithium fluoride. Yeah. Now, what that means is if we do that, is if the lithium loses its electron over there, that means that lithium becomes a plus. Because if you think in a normal atom, a normal element, a normal atom, the number of electrons and the number of protons balance out, so there's no overall charge. But the moment you start changing these, if you remember rightly from earlier when we were talking about ionic states, by altering the number of electrons, you can either add them to make it a negatively charged atom, and therefore what we call an anion, or we can reduce the number of electrons such that the protons then become more numerous, and therefore it becomes a positively charged called a cation. So what we've done here essentially is we've created two ions, and we've got fluorine up here, which is a minus, and lithium up there, which is a plus, which means we now have lithium fluoride, which means we've looked at our first chemical reaction, guys, and we've looked at how that works at the very basics. So what that now gives us is the fluorine has now got its full 8 octets, as we call it. So second shell is now full, courtesy of lithium. Lithium has made an investment with fluorine and made fluorine into a fluoride, and given fluorine its outermost full shells. In return for that, lithium now just has the 2 electrons in the inner shell. It has to remain with fluorine, of course, because now it's made its donation. They've now got a happy marriage. They have now formed what we call something called a compound. That is another term that you will meet on a regular basis. And if you remember as well, I said that lithium plus would be a cation, because all charged metal atoms are what we call cations, and that one over here would be called an anion. So I'm hoping this kind of wraps up the last couple of videos that we've done to try to introduce how this is beginning to work, because where I want to get to next is to talk about the periodic table now and show how these shells increase and decrease in terms of being filled up, intrinsically looking across the periodic table. And you're only going to see that when you look at the periodic table. But I would like to draw your attention to the fact that I have done an interactive to show this, which I'll provide the link underneath this video for you to take a look at, where we can look at electronic configurations, and you can see a bit more about how that interacts with the atomic number and the atomic mass. So what I'm going to be doing after this is looking at the periodic table and looking at some reactions. So we now know about filling up the shells. We now know that what the atoms would like in an ideal world is to fill their outermost shells or lose the other electrons, that whichever's easiest for them is the path they're going to take. And that is the basis of what chemistry is. It's the atoms striving to complete their outer shells in one way or the other, either by emptying out the excess or bringing in what's needed to fill, as you can see here. Anyway, I'm not going to ramble on any longer. I hope that part makes some sense, and I look forward to seeing you at the next video. Take care till then. Thank you.